In working with optimization, it's a lot like working with related rates. There is kind of a sequence of steps that you generally go through. And so first thing is read, of course, read and read carefully, draw a diagram, introduce notation, and then really identify what you need to find. Form an equation between the quantity you want to maximize and other knowns. And then the fifth is your constraint equation. In the previous video I used the equation of auxiliary. And that auxiliary equation is a constraint equation. It's just saying you have to have this condition in order for the problem to go, for you to be able to solve the exercise. Okay, but you're going to apply the constraints and then locate the absolute min or max or local min or max depending on the problem context. Okay, ideally it will be the absolute, but we'll have to verify that in each context. Okay, so let's see our first example. Okay, so I'll let you pause the video and read it if you need to. But the idea is that we have a piece of cardboard and we want to make a box out of it. Okay, and what we're going to do is cut out squares from each corner, and then fold it up along the kind of creases and make a box. So the idea would be, here is our piece of cardboard. It is a square, and we know the width here is 3 feet. And this is also 3 feet, hence it's a square. Okay, but what we're going to do is we're going to cut out little squares from each of the corners. And what this will enable us to do is we can then fold along the lines that connect the vertices of those squares that we cut out. We don't know how much those squares we cut out are, but their sides are all X. And then we fold up along the dotted lines to make an open top box. Okay, and our goal is to find the largest volume. Okay, so I don't know what volume is. Okay, but I do know that the volume, this would form a rectangular prism, right? So I would fold it and it would look something like this, where the width here would be 3 minus x because or 3 minus 2x, I'm sorry. And then 3 minus 2x, and then this would be x. Okay? And so the volume here, since this is a rectangular prism, would be, length times width times height. Okay? The length here is going to be 3 minus 2x. And then the width is 3 minus 2x. And then the height is x. Okay? Now, where I said before that we were going to have a constraint equation. Well, where is that? That's actually implicit here by the 3 minus 2x's. Okay? We're using the constraint of the surface area. Okay? So anyway, going forward, we would, distribute this. This would be 9 minus 12x plus 4x, and then all that times x. So really and truthfully, it's 9x minus 12x squared plus 4x cubed. Okay? And so then with this, now I'm ready to say, okay, well, I want to use previous methods to locate the absolute mins and maxes. Okay, well, before I go forward, it might be useful for me to identify, am I on a closed interval or for an open interval? So if I think about x, what are the values that x can take on? Well, x, it has to be bigger than 0, right? Mainly because, well, if I had x as 0, then I don't have anything, I can't fold it up. And similarly, x cannot be more than 1.5 because otherwise I have to cut x from each side. I'd be cutting off the entire thing, right? So, and then I'd have nothing left. So x has to be somewhere in that region. Okay, so just keep that in mind as when you're working through these problems, thinking about the domain might be useful. Okay, but nevertheless, I'm not on a closed interval per se. I kind of am, but I'm not really. So I can't use the closed interval method, but I can still look at the derivative of the function and find the critical points. Okay, so I'm going to look at v prime of x. Okay, this ends up being 9 minus 24x and then plus 12x squared. Okay, and I can find the critical numbers by setting it equal to 0. Okay, divide everything by 3, and I get 3 minus 8x plus 4x squared. And how do I go forward? I try and factor. It does factor, and then consequently I get the critical numbers as x is equal to 1/2 and x is equal to 3/2. Okay, and well, sad thing is I have to toss out the 3/2 because that's outside my domain. Okay, so x equals 1/2 is my only critical number. Now, you would assume that this, okay, you got a critical number and there's going to be a local max or min or something here, but we should verify. Okay, now remember to verify a maximum or a minimum, local, that is, local max or min, you can either do the first derivative test or the second derivative test. Here, I'm going to choose the second derivative test only because my first derivative is a nice polynomial function. So if I compute the second derivative, right, that's going to be, and I'm going to rearrange 24x minus 24, and then I have to substitute in the critical number that I found, and so then I get minus 12, which is less than 0, right? So then by the second derivative test, this implies that x, or that 1/2, and then v of 1/2 is a local maximum, and then second derivative test. Okay, so you do have to verify even after you've maybe classified or you found a critical number that it is what you think it is, just to make sure that everything is good. Okay, now after this, so I'll tell you that doing this sort of verification is the #1 thing that students forget. Okay, but then the second thing that they forget is like, oh, they got an x value and they're done, right? Well, am I done, right? I have to reread the problem, find the largest volume. Okay, I'm not done because I have to find the largest volume. Okay, so I need to say, come over here, and I need to say v of 1/2 is, and I should have found it earlier, I didn't, but it would have been 9 times 1/2 minus 12 times 1/4, and then plus 4 times 1/8. Okay, 9/2 minus 3 plus 1/2, okay, and I get 2. Okay, so then I just have to write my, since this was a problem in context, you need to respond in context. The maximal volume of the box is 2 feet, cubed. Okay, it is a volume, so you need cubic units. Okay, but now to recap, what did I do? I started off with a diagram, right? So that's on #2. I introduced notation, right? V, and then I formed an equation. Okay, so that's this part in blue. Okay, I identified it and identified constraints by recognizing that each of the sides, once I cut out x from each side, is going to leave 3 minus 2x for the width of this base. Okay, so that was my constraint. And then with this equation, I found the maximum and minima using the first derivative, or second derivative test by first finding critical numbers and substituting those into the second derivative. Okay, I did recognize that I was not on a closed domain, so I don't need to check the endpoints. And then lastly, just make sure to answer everything that you are being asked for in the problem.